All right, so you know how people are always talking about AI being amazing at stuff like, crushing it at games or driving cars around?
Hmm.
Well, today we're diving deep into how that actually works. And it's all thanks to something called reinforcement learning, or RL for short.
That's right, RL.
And RL is basically like, it's almost like teaching a computer or an AI to learn through experience,
Yeah.
right? So, rewarding it when it does something good and maybe giving it a little nudge when it messes up.
Yeah, exactly. Like you said, it learns through interacting with its environment.
Okay, so like a digital pat on the head or a little,
Little zap.
exactly.
Yeah.
So before we get too deep into this, I think it would be good to get a little context, right? Like, where did this whole idea of teaching AI through feedback even come from?
Well, believe it or not, the roots go way back, even to the early 1900s, like 1905.
Wow, that's,
Yeah, Edward Thorndike, a psychologist, he observed something he called the law of effect, which basically says that actions followed by good outcomes, well, they're more likely to happen again.
oh, okay, I see.
It's like, when you train a dog with treats,
Oh, yeah.
that's the law of effect in action.
Okay, so that's actually really interesting, right? So we're talking about AI, but we're starting with, like, basic psychology.
Right. And even, Pavlov's work with dogs and bells,
Right, yeah.
that whole classical conditioning thing plays a part in understanding how learning in general works.
Okay.
But things really took a turn toward, modern AI in the mid 20th century, like around the 1950s, with a guy named Richard Bellman.
Yeah.
He was a mathematician, and he came up with something called Markov Decision Processes,
Yeah.
or MDPs.
MDPs.
Yeah, and this was a way to actually model decision making in a mathematical way, especially when those decisions happen over time.
Oh, wow. What
And
thing?
part of this was his famous Bellman equation, which is still really important today in RL.
So this is where the psychology and the math really start to come
Yeah,
together.
absolutely.
And this leads us to the RL that we use, in AI today.
Yeah, so in the late 20th century, we saw some really key algorithms developed. There's temporal difference learning, or TD learning, which came out in 1988.
88.
It let AI learn from even partial experiences, which was a big deal.
Mm,
And then in 89, we got Q learning, a way for AI to figure out the best way to act in different situations.
okay.
But here's where things get really mind-blowing. Fast forward to 2015, DeepMind, you might have heard of them.
Yeah, they're doing some crazy stuff.
They built an AI that learned to play Atari games, those old school video games, at a superhuman level. And get this, just by looking at the screen,
What, just from seeing it?
just from the visuals.
That is insane.
Imagine learning to play a brand new game without any instructions, just watching.
That's incredible. So you mentioned the brain earlier, right? Like with psychology, does that tie in here at all? Like, are there any more connections?
Oh, yeah, definitely. So remember operant conditioning? That's B.F. Skinner's work, how rewards and punishments shape behavior. That's basically what RL is doing.
Oh, that makes sense.
But the connection to neuroscience is even cooler.
Okay.
Our brains release dopamine when we experience something good, right? Like a reward. But get this,
What?
it releases even more dopamine when we get something better than expected,
Oh, interesting.
like a surprise reward.
So it's not just about the reward itself, it's about how unexpected it is.
Exactly. And that difference between what we expect and what we actually get is called reward prediction error, and that's a key signal in how RL algorithms learn.
Whoa, so the AI is mimicking like a fundamental part of our brains.
Right. It's mimicking how our brains learn through reward.
It's kind of mind-blowing. So, okay, let's break down the essentials here. What are like the key concepts that we absolutely need to know to understand how RL works?
Okay, so first you have the agent. That's like the AI, the learner.
Okay.
And it exists in an environment, which could be anything, a game, the real world.
All right.
At any given time, the environment is in a certain state, like the position of pieces on a chessboard. The agent takes an action, like moving a piece, and that action changes the environment's state.
Mm-hmm.
Then the environment gives the agent a reward, which could be positive or negative, and that tells the agent how good or bad its action was.
Okay.
The agent's ultimate goal is to learn a policy, which is basically a strategy, a way of choosing actions in each state to maximize its total reward in the long run.
Got it.
Sometimes an agent might use a model to try and predict what will happen next based on its actions.
Like a little simulation in its head.
Exactly.
Right.
And we also have something called a value function, which tells us how good a particular state is.
So a state with a high value function is a good place for the agent to be in.
Exactly. It means the agent expects to get a lot of reward from being in that state.
Got it.
Then there's the Q value, which is like the value function that's specific to a particular action in a particular state.
Okay, so it tells us how good taking a specific action is in that state.
Right. And finally, there's the discount factor, which is how much the agent cares about future rewards compared to immediate ones.
So a high discount factor means the agent is thinking more long-term.
Exactly.
That makes sense. So we've talked about Markov decision processes a few times now. Can you remind us again what that's all about and why it's important in RL?
Sure. So think of that simple board game again, right? The current layout of the board, that's the state.
Okay.
Your possible moves, those are the actions.
Okay.
The rules of the game, that's the transition model, which basically says how likely you are to go from one state to another after taking an action.
So it's like the physics of the game world.
Yeah, exactly. And then there's the reward function, which tells you how many points you get for different outcomes, like winning the game.
Okay.
But the really important thing here is the Markov property.
Okay, what's that?
It basically says that what happens next only depends on the current state of the game, not the entire history of how you got there.
Oh, okay. So it doesn't matter how many times you've moved your piece back and forth.
Exactly. It only matters where it is right now.
That simplifies things a lot.
Yeah. It does. And it allows us to use powerful algorithms like value iteration and policy iteration to figure out the best way to play the game.
The best way to play, so we've talked a lot about the theory, but where are we actually seeing RL in action in the real world?
Well, like we said earlier, gaming is a big one.
Right, with AI mastering those really complex games.
Exactly, like AlphaGo beating the world champion at Go.
Right, and what about outside of gaming?
Oh, tons of places. Robotics is another huge area where robots are learning to do all sorts of cool stuff.
Like what?
Like learning to walk, learning to grasp objects, learning to navigate complex environments.
Oh, all through RL?
Yep, and then there's autonomous vehicles.
Oh, yeah, self-driving cars.
That's a really hot area for RL because you need to make all sorts of decisions on the road, like when to change lanes, when to brake, when to accelerate.
Oh, yeah, those are like life or death decisions.
Exactly, and RL is helping cars learn to make those decisions safely.
That's really impressive. What about in other industries?
Oh, it's popping up everywhere. Finance is using it for algorithmic trading. Healthcare is using it for personalized medicine, like figuring out the best treatment plan for each patient.
Wow.
Recommender systems, like what you see on Netflix or Amazon, they're using RL to figure out what you might like.
Oh, so that's how they suggest stuff to me.
Exactly.
That makes sense. And even energy management, like figuring out how to optimize the power grid.
That's right. So RL is really becoming a versatile tool across many different fields.
Yeah, it sounds like it. So with all this potential, what's next for RL? Where do you think it's going?
Well, one of the big things is improving sample efficiency, which means getting RL to learn from less data.
Oh, okay, because right now it needs a ton of data, right?
Yeah, like imagine training an AI to play a game by letting it play millions of times. That's a lot of data.
Yeah, that would take forever.
Exactly. So we're trying to figure out ways to make it learn faster with fewer examples.
That makes sense.
Another big area is generalization, which means getting RL to work well in new situations that it hasn't seen before. Okay. Like if you train an AI to play one video game, can it then play a different video game without having to learn everything from scratch?
So it's like, can it transfer its knowledge?
Exactly. Can it adapt?
Okay, that's a big challenge, I bet.
It is. And then there's a multi-agent RL, which is about getting multiple AI agents to work together.
Oh, so like a team of robots.
Yeah, like a team of robots that have to coordinate to achieve a common goal.
That sounds really hard.
It is. It's much more complex than just having one agent acting on its own.
Right, right. So what about other challenges?
Well, we've talked about sample inefficiency, needing lots of data.
Yeah.
There's also the challenge of exploration versus exploitation.
What's that?
It's about finding the right balance between trying new things and sticking with what you know works.
Oh, okay, I see.
And then there's reward engineering, which is figuring out how to design the reward system so that the AI learns the right behavior.
Because if the reward is wrong, the AI will learn the wrong thing, right?
Exactly. And then there's the challenge of stability,
Stability.
making sure that the learning process is stable and doesn't, go haywire.
Oh, okay, that makes sense.
And then there's interpretability, which is understanding why the AI is making the decisions it's making.
Oh, yeah. That's important, especially if we're going to trust AI and make important decisions.
Absolutely. And finally, there's the challenge of safety and ethics, making sure that RL is used in a way that is beneficial to society and doesn't cause harm.
Right, so there are still a lot of challenges to overcome.
Yeah, there are, but it's a really exciting field with a ton of potential.